Hi ladies, today we're going to start finally talking about chemicals, and the type of chemicals we're going to talk about today are ions. Now, to understand what an ion is, you first have to figure out what makes up an ion. So valence electrons are the electrons on the highest occupied energy level of an element's atom. And it pretty much determines all of the chemical properties ever about that element. So for example, if you were to look at sodium, which is Na, your electron configuration for sodium would be 1s2, 2s2, 3s1. So whenever you look at this electron configuration, you look at your highest energy level, which is your number 3, because that's your biggest number, and then it tells you how many electrons are in there, which is 1. So the valence electrons for sodium would simply be 1 valence electron. An easier way to do that, instead of making all of those electron configuration, is to simply look at the group number. So if you were to look at your periodic table and trace your finger all the way up to above hydrogen, you'd see the number 1. In that column, in that entire row or column down, all of those would have the same group number, and therefore they have the same number of valence electrons. So for example, if you were to look at lithium, sodium, potassium, rubidium, cesium, all of these are in the same group, and they all have the same number of valence electrons, which would be only 1. So they go into detail about how the group 1 is always going to have 1 valence electrons. If you start to go over a little bit farther, such as in group 4A or maybe number 14 on your periodic table, depending on what you're looking at, that will be showing you 4 valence electrons. Your noble gases, which are all the way to the right, those guys are the only exception to our group number rule. The atoms of helium, so helium is He. That would be this guy, he's He. He only has 2 valence electrons because that's all the more electrons he can have. And the atoms of all the other noble gases have 8 valence electrons, which happens to be the same as your group number of 8 up here. So whenever you're using these valence electrons, a lot of times you want to show them in an electron dot structure. And an electron dot structure is simply a diagram that shows the valence electrons of that atom as, if you can guess it, dots. So if you take a look at this nice little chart here, it goes through a couple of the different valence electrons or the different electron dot structures of some of the things that you find on your periodic table. And the one thing that is really important is how to put those dots into this structure. So let's try looking at magnesium. So that would be this guy. Magnesium has 2 valence electrons because it's in group 2. So there you go, group 2A. So first you would write the symbol, and then you would start to add in your dots. It doesn't matter where you start, as long as you go in singly. And what that means is, let's look at sulfur here. It's in group 6, so it must have 6 valence electrons. I'm going to abbreviate that as VE, valence electrons. So let's try and do that one. So once again, you're going to draw your symbol, and now we need to put all those 6 valence electrons around it. So we start by going in singly, and then doubling up just like we did before. And it doesn't matter where they double up, as long as you rotate around clockwise and don't change directions, you'll be set. And the whole reason that they want to do this is so that they can get something called the octet rule. And what the octet rule is why they start to act certain ways. They want to get as many electrons as close to a noble gas as possible. Our noble gases, such as, helium, neon, argon, krypton, all of those guys are extremely stable because they have a full valence electron shell. So those guys actually don't even react with anything. So what they want to do, what our other elements can do, is they can start to lose electrons or gain electrons. And their whole focus is to get to the octet rule. Octa means 8. 8 is going to be our focus. We want to get our 8 valence electrons. Sometimes that means we will gain electrons, or we can lose electrons. It depends on how close they get to that noble gas. All right, so let's try drawing our electron dot structure for bismuth. So let's see here. We need bismuth, which if you want to find it on your periodic table, it's going to be in group number, let's see, number 5. So in group 5A, or if it's on a different periodic table, it could also be a number 15. So if you want to, we got to figure out first our valence electrons. So the number of valence electrons in group 5 is 5 valence electrons. So now we're going to draw our electron dot structure. So first we draw our symbol Bi, and then we start to add all these 5 valence electrons around the outside. So we start going singly. So there's our 4, and then we start to double up, and there's our total of 5 valence electrons. And a little bit better drawn is right here by the computer. We're trying to get towards that octet rule, so sometimes you have something formed called a cation. Cations are what occurs whenever you are going to lose electrons. So whenever you have a positively charged ion, that means you have lost your electrons. So you have lost one or more valence electrons. So let's take a look at sodium. Sodium looks like that. It's in group 1. So it has 1 valence electron. Now, it can do one of two things. It could, all right, so it can either gain 7 electrons, so it looks something like this, where it has all 8 valence electrons around it, or it could lose 1 valence electron, and that way it would look like a solid sodium, but it would also look a lot like the noble gas neon. So let's take a look at what it would do by drawing its electron configuration. So remember we have so I took away that stuff at the top so we had a little bit more room. So remember Na, our regular electron configuration would be 1s2, 2s2, 2p6, 3s1. Now remember our two options is it could either gain 7 more electrons or lose just 1. And personally, I'm pretty lazy, so I'd rather lose just that last outer edge valence electron to make it look like the following electron configuration. Now, if you were to look and do the exact same electron configuration for neon, neon looks exactly the same. So that must be what we are doing. We're only going to lose that 1 valence electron in order to look just like neon. However, now we're going to have a charge. So now instead of it being neutral, it will be sodium plus 1. So most cations are going to be produced by the loss of those valence electrons. They're typically metals, so they're going to be on the left side of your periodic table. So if you need a reminder, if you're looking at your periodic table, you have the stair steps over here of your metalloids. They're going to be all these guys. All these metals are going to be losing your valence electron. And they are pretty easy to remove those electrons because they want to look like those noble gases. It makes them more stable. So when forming a compound, however, it's going to lose that valence electron to make it look as if it is that noble gas. Usually it's going to donate it to somebody else, and we'll see that here pretty soon. And the number of those protons in the sodium nucleus, it never is going to change. So we can calculate the overall charge, or if you remember that losing our electrons is going to give us a positive charge. If you want to look at the orbital diagram, you can kind of see how it is going to play, how it plays into these electron configuration. So on the left, you have sodium's atom, which has all of its electrons shown. And you see that top electron being all lonesome all by itself. So you could either gain 7 more to fill that octet role, or simply lose that one. It causes it to have a positive charge because remember, losing an electron means that you are going to become positive. And if you were to compare it to that of the orbital diagram of neon, they look exactly the same. That's because they are. However, the number of protons, remember those are the positive guys in the nucleus, the number of protons has stayed the same. That's what makes our two elements very different. The same can be said about group 2, but remember magnesium is going to be, it has 2 valence electrons, so it's going to have to lose more electrons. So let's look at magnesium's electron configuration. So, oops, sorry about that. So you have magnesium, its electron configuration is 1s2, 2s2, 2p6, 3s2. So we can either gain 6 more electrons or simply lose 2. Remember, we like to be lazy, so let's lose those outer 2 electrons to give us the electron configuration close to neon once again. However, because of the number of protons, we're going to get that positive charge. So since we lost 2 electrons, our charge is now going to be a positive 2. And that's shown down here as well. Whenever you lose those valence electrons in your electron dot structure, it is going to create that positive 2 charge. So if you want a nice diagram to remember all of the charges and how it will react with the first 2 groups on our periodic table, it is here. However, remember that our group number is going to tell us how many electrons we're going to gain, how many electrons we're going to lose, because we want that full octet. All right, I'll see you next time. Have a good one.